It has to be infinite. Router 8 will still have infinite because we still have to go through about, let me see, 1, 2. 2 more routers just to get to 8, which we don't have in our node iterations. The same applies to router 9, so infinite as well. Router 10, infinite. Now we have router 1, 2, and 4. Wow, so now we're gonna slow down some of these infinite values. So now we have 1, 2, and 4 to forward packets. So that's a lot more options now. It's kind of like a concept of using going to a trotro station and then having multiple routes to a given destination. That's the concept over here. So if you now have all different cars going to multiple destinations, you have options. You don't have to wait in one car anymore for a long time until it fills up. You can just go for the other car that's about to move. Or if you're standing by the car junction and you're going to maybe Achimota, see a number of cars come. You have options now. You don't have to wait for one to fill that first. No. You go, Madina, sorry. You're gonna have La Paz, or Achimota. So you have cars coming through. That's what we do over here. The nodes are the cars coming in. Options. So with the first one, we only had one car. That's why we had to have infinite, because we had to basically use one device to move the packets. We have three nodes. We have 1, 2, and 4. So we have 1, 2, and 4 to 4 packets. So let's see what the numbers will be like. Router 1 will still be 1. Router 3 will still give you 3. Router 4, so let's 4. We'll still give you the 2 here. So it'll still be 2. Router 5 will still give you a 2 because it's 1 plus 1, 2. By router 6, it will still be infinite because even though we have 1, 2, and 4, 6 in the middle over here, we have to go through either 3 or 8, and we don't have that. We don't have 3, we don't have 8. So 6 will still be infinite. Now watch 7. 7 used to have 8 as the cost associated with it. But now watch, we have now that we have options, look at the cost now. We can go from R1 through R4 to get to R7 and use a minimum cost of just 2 and 1, which is 3. Before that, we didn't have 4, so we can only move from R1 to R7, and it had a cost of 8. But now that we have 4, we can move from what? R1 to R4 to R7, and the cost is 2 plus 1, which is 3. So now it changes to what? 3 as the least cost now. Okay, great. So that's a good question. Comfort, I like the question that you asked. Why did I move straight from from 1, 2 to 4 nodes instead of 1, 2, and 3? Well, I'm looking at the devices that I'm directly connected to, my closest neighbors. Okay, and if you look at it, 1, the closest neighbor that it has is 4, 3, and 7. Are the closest neighbors that it has. Comfort, is that clear? So that's why I use 1, 3, so 1, 2, and 4. Because 3, I would have to go through 2 to get to it. I'm not directly connected to 3, so I can't go ahead and include 3 right away. That's why I didn't go 1, 2, 3. I'm using my closest neighbors to move my packet. Or the neighbors that I'm directly connected to. And in this case, it was 1, 2, and 4. So that's why I have 1, 2, and 4. Okay? So for 8, it will still be far away. It will still be infinite. 9, the same thing, will still be infinite because I'd have to go to a number of routers just to get to it. And the same applies to 10. Now we have 1, 2, 3, and 4. I've included 3 now because now I'm moving away from my closest neighbors now because I've already covered all of my closest neighbors. The subsequent or the reasonable node to go through is the third one. So now I have 1, 2, 3, and 4 to move packets now. So I got 1, 2, 3, and 4. Great. So 1 was to router 1. To move packets to router 2, it will still be 1. To router 3, it will still be 3. Sorry, 3. To router 4, it will still be 2. 2 is still the least cost. To 5 is still 2. Now let's watch 6. See, now that we have 3, we can get to 6 now. See, bingo. See, now that we have inclusive, we have 3 inclusive, we can get to 6 easily because 6 is directly connected to 3. So now if you want to move packet to 6, it's possible because now you can move it from R1 to R2 to R3 to R6. Now look at the cost involved. From R1 to R2 is 1. R2 to R3 is 2. That's 3 right there. From R3 to R6 is 2. So that's 3 plus 2. That's 5. We have 5 here now. So now we can get to 6 by a cost of 5, a least cost of 5. Well, a cost of 5 for now, at least. We've not tabulated, we've not really accumulated a least cost yet. We are just putting together a cost. So we have a cost of 5 now. Before the first 3 iteration, it was all infinite. Okay. And then 7, we still have 3 as a least cost now. What about 8? Can we still get to 8? No, we can still not get to 8 because to get to 8, you'd have to go through 6 and 5. We don't have 6 and 5. So it'll be infinite. Infinite, infinite. Okay, so now let's include 5. Now I'm making a sequence of 1, 2, 3, 4, 5. So now I have 1, 2, 3, 4, 5 nodes to move the packet. So you're going to realize that now I can get to a lot more of the other network devices that are further away from me. So I have 5 nodes or routers to use to forward the packets. So you're going to notice a huge difference in the infinite values now, or cost. R2 will still be 1. Oh, oops. It'll still be 1. R3 will still be 3. R4 will still be 2. R5 will still be 2. R6 will still be 5. R7 will still be 3. Now watch R8. Since we have 5 in our iterations now, we can get to 8. Okay? And so we can go through this route, R1 to R2 to R5 to R8. The cost is 1 plus 1 is 2. 2 plus 2 is 4. So it will now be 4 here to get to 8 now. Are we following, guys? Are we following? This is a fun start. This is a fun stuff about routing. This is how your packets are routed on a network. This is how the router makes decisions on how to route the packets. That's what they're doing in the back end, in the algorithms. That's what they're doing. They're looking for what's the quickest way to get to, the next hop. So we can forward packets, to the final destination quicker, faster. So, you're happy with the connectivity. I'm getting information quick. They're thinking on their feet. Routers are thinking. Routers, they think a lot. They're always thinking, speed, quick. The very moment they slow down, we get frustrated. Oh, it's slow connectivity. I can't see the screen, it's blurry. You start getting issues like that, okay? So if you have good routers with good costs associated with them, you're not going to get blurriness on your screen. You're going to see what I'm doing clearly. And they're going to be flowing, with speed, clarity and fastness. There wouldn't be any buffers or jitters in the transmission. So your router is thinking. Like for instance, over here, to get to R1, it was using cost of 8, a higher cost. But when it got to iteration 3, and it had 3 routers or nodes to work with, what did it do? It recalculated its cost and realized it'd be much cheaper to go through 1, 2, 4, 2, and 4 and have a least cost of what? Or a cost of 3 instead of a cost of 8. So now that's basically renegotiated its cost. You get it? Sometimes you might have, you might go through multiple routes, nodes to get a least cost. You might think that if you move through maybe 3 or 4 nodes, I should give you a much more higher cost. No. Sometimes even 5 cores will give you a least cost as compared to just one iteration on one node. No, Louis, this is supposed to be a complex internet, okay? I'm using this in such a way that when you look at it, it gets you thinking. You have to be looking at what's going on in a diagram. If I use 5, it's too simple. You wouldn't get a much elaborate, iterations. But if you use only 5 routers, it would be too simple, too simplified. When you have more than five, yes, it gets complex, and then you can be able to think through the iteration very, very well and be able to deduce the costs that are associated with the route. Anyways, let's deal with this. It's much better this way. This is the best way to understand this, okay? Now, to start with a smaller, it wouldn't be too... Louis, start thinking, man. Start thinking. Get with the program, okay? Get with the program. Okay, so moving on. To get to 9, it will still be too far away. So it will still be infinite. 10 will still be infinite. Wait. 10. Now watch. And we can get to 10. Plus we have 5. There's a connection from 5 to 10. See that? And it has a cost of 5. So it'll be 5 plus 1 plus 1, which is 7. So now to get to 10, it's 7 costs. Okay? I'm going to give you guys a diagram to play around with it. We're going to your assignments before we have our final exams. Okay? As a homework, you go sit down and you tabulate from every node. And that will be a 20-point assignment, 20 huge points. Okay? So if you're connected to router 1, tabulate all of this. For router 2, tabulate it. Router 3, tabulate it. If you're connected to any of the routers, tabulate all of the costs associated. Theophilus said, so the purpose of using Dijkstra algorithm in this question is to find the path of least cost from node 1 to any other node within the network, not just from 1 to 10. It's from 1 to every other node, so that 10 inclusive. Gotcha, so there is, exactly. So it's not from node 1 to 10. It's from node 1 to every other node within the entire network. Because if I had said from node 1 to node 10, it would probably be just from 1 to 10. But there are other nodes involved, so we can't say, so that's why I use the word every other node within the entire network. Maybe in English form, maybe you can say that from node 1 to node 10. No, that's not the word. It means that I'm only connected from R1 to R10. That's what your question means. But that's not what we're looking for. We're looking for every other one, or every single device, every single node within an entire network. So from node 2, 3, to 4, to 5, to 6, to 7, to 8, to 9. So maybe your question should have been this. From node 1 to 2, to 3, to 4, to 5, to 6, to 7, to 8, to 10, all the way to 10. Theophilus, is that good? If you say it that way, it will make sense. Yes, it will make much more. Otherwise, if you say just from node 1 to 10, and you know, students, they're going to say, okay, it's only from 1 to 10. What about the other ones? So it will bring confusion. But if you say from node 1 to 2, to 3, to 4, to 5, to 6, to 7, to 8, to 9, to 10, then it makes sense. You go, oh, okay, every one of them. Yes, every one of them. There you go. Okay, great. So where were we? Now we are on our sixth iteration, which is actually 5 in terms of the numbering, since we started with 0. Now we have 1, 2, 3, 4, 5, 6 nodes to work with. So now we have 1, 2, 3, 4, 5, 6. So now we can get to 10, and probably we still can get to 9, because 9 is within these two guys. Anyways, so for 2 we still have 1. For 3 we still have 3. For 4 we still have 2. For 5 we still have 2. Now for 6 we still have 5. Yes, since we're still using, yes, we still have 5. Yeah, to get to 6, it's still this way. From 1 to 3, sorry, 1 to 2 to 3 to 6. What about 7? 7 is still 3. 8 will still be 4. 9 will still be infinite, because it's still further away. You have to go through 8. And we don't have 8 in our iteration. So it will still be infinite. Or we can still get to 10. And that is what? 7. Well, currently it's still 7. Okay, now moving on to the 7th iteration with a value of 6. Now we have 1, 2, 3, 4, 5, 6, and 7. There you go. So now we have 7 inclusive. Now let's see if we can get to 10 at with a much cheaper cost. Okay, so I'm going to start with 10 first. So let's go through that. Before that, it was 7. From 1 to 10, it was 7. Let's see, now that we have 7 inclusive, node 7 inclusive, it means now we can actually reduce the cost. We can actually go from router 1 to router 4 to router 7 to router 10. And the cost is 2 plus 1 is 3 plus 1 is 4. So now we jump from 7 to 4 now. Before that was 7 because we didn't have router 7. So we only have to go from router 1 to 2 to 5 to 10. But now that we have 7, we can go this way, this direction instead. 1 to 4 to 7 to 10. See, Pat? Routers are thinking, they're smart. They're thinking on their feet. Finding you the best suitable cost that they can move your packet for you. So your Facebook profile can stream. It can come to you very quick. Fast. That's what they're doing. Are we good? So when I realized that, oh, it's much better to use 4. The rest will still have an infinite value. Now it will still be infinite. And I think the rest will still maintain their values. So there's going to be 4 here. There's going to be 3 here. There's going to be, now let's check on 6. 6, since we have 7 now, let's see. Watch. We can get to 6 at a much cheaper cost. Now, instead of going from R1 to R2 to R3 to get to R6, we can go this direction instead. R1 to R4 to R7 to R6. And the cost is 2 plus 1 is 3. 3 plus 1 is 4. So this will be 4 now. See, it has changed from 5 to 4 now. The rest will still be 2, 2, 3, and 1. See, this is fun stuff. This is the coolest stuff ever, man, guys. This is fun. Routing is fun, man. Now you're understanding how the router is thinking. So when you're getting all those, good response for your request, you have to understand that the router is thinking. You have to understand what's going on with the router. Why it's thinking that fast? Or what's going on in the back end? The Dijkstra algorithm is working to your advantage. Folks, you're catching on. This is fun stuff, man. It doesn't get any fun than this. You gotta appreciate networks and implementation. Whoever built some of these algorithms was thinking way ahead of time, just to make sure that people can enjoy the internet or a connected network. Are we good, guys? Okay, so now we have more iterations now. Well, we have more nodes in our iterations. We have 1, 2, 3, 4, 5, 6, 7, and 8. So now let's see if now we change now. Since we have 8 at our disposal now, we can get to 9 now. See, now we have 8 inclusive, we can get to 9 easily. So it means now we don't have an infinite value anymore. We actually have the cost. So this will still be 1, 3, 2, 2, 4. Yes, still be 4, 3, 4 again. And then now we'll now have, let's check what will the cost now. So it'll be from R1 to R2 to R5 to R8 to R10, sorry, to R9. So it'll be 1 plus 1, 2, 2 plus 2 is 4, 4 plus 3 is 7. So now this will be 7 here. And this will still be 4. So now we've known that we've basically eliminated all the infinites now, thanks to the fact that we have what? This number of nodes at our disposal. So to basically be able to forward packets to all the other nodes within the network without getting an infinite cost, you would have to have node 1, node 2, or router 1, router 2, router 3, router 4, router 5, router 6, 7, and 8 at your disposal within your iteration sequence to be able to reach every other node within a network. Are we good? So before that, if you were connected to router, if it was a customer over here, if you're a customer connected to router 9, if I wanted to forward you packets, it would be difficult because I wouldn't have my much of iterations to work with. I would have to work, the only way I can send packets to you is if I have 1, 2, 3, 4, 5, 6, 7, 8 routers in this sequence at my disposal before I can actually forward packets to you. So if you're a client, so you are one of you guys, you're connected to maybe MTN, so this is Vodafone, right? So Vodafone over here, then that's what will happen. It will take you forever. You know, it will take you a number of iterations before people can actually forward packets to you. Okay, so now we have a clean slate of all the costs to get to every other node. So the rest will just be more of a streamline, right? Okay, so this will still be 1. So now that we have 9 inclusive, we have 1, 3, 2, 2. What is 4? I think this will still be 4, right? Yes, it will still be 4. 3, based on a diagram. Yeah, it will still be 3. 8, would 8 reduce? Let me see. 8 reduce. Now that we have 9, no, it will still be the same 8. It's the same 4, sorry. What about 9? Would 9 reduce? Now we have 9 inclusive. Not really. It'll still be 7. What about 10? 10 will still be 4 because we're still going through either 5 or 7. Actually, which 7? 5 gave us a higher cost of 7. But with 7, we had 4. Okay, and then finally, the same thing across. So it will still be 1, 3, 2, 2. I think it will still be 4, 3, 4, 7. Yes, 7 again. And then finally 4. So now that's your tabulated Dijkstra algorithm cost associated with this particular network. Now we need to highlight the least cost now. So now Dijkstra is all about the least cost. We basically tabulate all the costs associated with moving packets from router 1 to every other router within the network. Now let's try and identify the least cost. Some of the costs were higher than subsequent ones. So for R1 to move packets from R1 to R2, the least cost is 1. So let's highlight that one. So let's put a highlight over there, green. So it means that you only need router 1 to get a least cost associated with moving packets to router 2. Since it's all 1 over here. For router 3, obviously this is all 3 here. The first one will be the least cost. That's the least cost. So it means you need router 1 and 2 to get a least cost to move packets from R1 to R3. Router 4, this is all 2. The first one takes precedent. Router 5, this is all 2. The same thing. The first one takes precedent. Router 6, it was 5, 5, 5 before 4. So we have to use this one. That's the least. And since it's all 4, this will be the least cost. For 7, it was 8, 8 before it became all 3s. So 3. For 8, 4 across, so it's that. For 9, it was 7 and 7 across. And for 10, it was 7, 7 before 4. So 4 becomes the least cost. So these are the least costs to get to all these other nodes. So now let's tabulate the route and the least cost and their next hops. Okay, but before that, let's try to draw the what's the name? Let's sketch the shortest path tree, because once you're able to identify the least cost, you're supposed to sketch the least cost path tree, the shortest path tree from the tabulation. So we go back to the drawing board. So in this case, all this craziness is gonna be much more cleaner. So this craziness over here, we're gonna have a much simplified much simplified diagram. So this here, much more simplified if you want to draw the shortest path tree from the tabulated Dijkstra algorithm. So the new Dijkstra shortest path tree would look like this. So let me go back to diagram. So now let's get rid of some of these things here. Let's delete some of these arrows. Let's get rid of some of these arrows. Some of these values. Okay, so from our diagram, from a tabulated output, to get to 2, it was only 1 to 2. So it means in our diagram, it would be 1 to 2. So label it. It was 1, right? So that's 1 to 2. The next one. To get to 3, you'd have to go through 1 and 2. So it means we need a diagram from, let me label the rest of the diagrams. So we have R5, undo. We have R5 over here. R5, it was R6 here, if I'm not mistaken. R6. We had R8 over here. R8. We got R9 over here. And then there was R10. R10. Okay, so to move packet to with the least cost to what? To R3, you'd have to go through R1, R2. So it means that actually this way, not this way. So we have to get rid of this one over here. So this one is to be deleted. And then the new one should have been from here to here. And the cost was, let me see, what was the cost? It was 3, right? So you had 1 over here, obviously 2's over here. So that's 2 here. Okay, what about 4? It was 2 and it had only 1, so it was just directly from here. It was 2, right? So it means this will be 2. So this will be 2 right there. What about 5 now? 5 now, it was 2, and you had to go through 1, 2 to get to it. So 1 and 2. So obviously, you have to connect this guy to this guy. And the cost was, since it was 2, it was 1, 1. There's 1 over here, 1 over here, which adds up to the 2 that we have, because it's 2 here. See 2, right? Going through 1 and 2. Going through 1 and 2 to get to 5. What about 6? We had to go through, the least cost was right down here. We had to go through 1, 2, 3, 4, 5, 6, blah, 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 blah. Lengthy one. So it means that it had 4, right? So there was, if I'm not mistaken, there was a connection from, since it was 4, the diagram again. Is it from here? It was from here to there, exactly. It was 1. It was 1 over here, 2 over here, and then there was 2 over here, which gives us 5. So it's 1, 2, 3, and 5. So tabulation for 6, we got to 4, right? So which means it was 7 that went through. Yes, it was from here. So it was 2, R4 to R7. 7 was inclusive, exactly. So we have to put an arrow for here and here, and the cost was 1, 1. If this is 2, 1, 1 to get to the 4. So an arrow here. So we had to have a cost of 1 here and a cost of 1 here as well to give us the 4 here, right? If you go through R1 to here, R4 to R7 was 1, R7 to R6 was 1. So 1, 1, 2, 4. So 1, 1, 2. Okay, so that's how you get to 6 with the least cost. So it was 2 plus 3 plus 1, 3 plus 1, 4. So how about getting to 7? 7 was 3 when we had 1, 2, and 4. We had 1, 2, and 4 at disposal. So it was direct from here. And the cost was 3, so which means this is 1. So it was 2 plus 1, that gave us a 3. What about 8? 8 is 4, and we had to use 1, 2, 3, 4, 5. So it means that it was 4, right? So it means it was from here, which is 1, 1. There must be 2 over here then. So we cross, and then we enumerate 2. So we had 4. 1, 1, 2, 2 plus 2 is 4. So that's a 4. Now we're using 1, 2, 3, 4, 5. There you go. So 1, 2, 5, all inclusive. What about 9? 9 was 7, and we had to go through a whole bunch of them. So it means that the best way was this direction. And since it was 7, it means that there's already 4 here. So this has to be a 3. Yes, it has to be a 3. There you go. So the arrow goes from here to here with the cost of 3 here. So that's 3 plus 2 is 5, plus 1 is 6, plus 1 is 7. That's what we had, a 7 as the least cost for 9. What about 10? It's 4, and we had to go through 1, 2, 3, 4, 5, 6, 7. So obviously 7 was the best route. So if it's 4, it means that since we already have 3 here, this must be 1 then. We had to go through 7 to get to 10, and this must have been 1 to get you to 4. So you have 1 plus 1, 2, 2 plus 2 is 4, giving us the 4 that we have over here. So now this is the shortest path 3 as compared to this one here. See how scattered it was? See how now the Dijkstra algorithm has gotten the routers to streamline their path. It's now much more simplified to the Luis guy. Is it? No, is it Luis? Yes, Luis. If we had used a match only 5, it would have been too simplified. It would be this direction. That's about it. It would have been this. You wouldn't see the beauty of how the routers go about with their elaborate cost calculations. So you see how we've reduced this whole directions and what have you to just a simplified one. See the beauty? Now, if you want to move packet to router 10, this is your packet you have. You can only go through this direction. Over here, you have so many. You can go from here to here to here to here or to there. You have so many. But with the Dijkstra shortest path and least cost, you have streamlined the whole. So now routers don't have to worry about going through this lengthy path just to get to 10 anymore. They only know that, hey, if I want to get to 10, I can only go from what? 1 to 4 to 7 to 10. R1 to R4 to R7 to R10. If I want to get to R6, it's R1 to R4 to R7 to R6. If I want to get to R3, it's R1 to R2 to R3. If I want to get to R5, R1 to R2 to R5. R8, same direction. R9, the same direction. A much more simplified routing algorithm or routing table. Thanks to what? Dijkstra shortest path, least cost algorithm implementation. Folks, there you have it. The beauty of what? Routing. The beauty of routing, folks. You gotta love routing. After this, you have to love it. Fall in love with it, man. Just fall in love with it. Okay? We've simplified all this craziness into a much, much more simplified shortest path tree. Okay? So now with this, we can go ahead and tabulate our route and least cost. So to get to R1 from customer, to get to from customer 1 to customer 2 connected to R1 to R2, it would be the least cost was going through R1. So if I want to go to customer, I'm using customers over here to illustrate a user over here. So a user is connected to a subscriber. It's connected to router 2. Maybe to simplify, let me use the router instead, the R instead. So we can actually get the picture. Hopefully you guys to catch on to this and be able to do this on your own. Actually, I prefer we use the customers because the information goes to the customers. So let's keep the customers. So customer 2 is connected to customer It's connected to R2. So all of these customers are connected to their respective corresponding routers. So in this case,